In our discussion on wave optics, we are continuing with the case of superposition or the interference of waves, and here we have the topic of coherent sources. Now, they are the, as you can see, the definition are the ones producing waves which are coherent. Now, what does the term coherent mean? Well, it means that the waves which are interfering here, we are always considering about the light waves. So the coherent waves here that we are talking about, they will have the same frequency. They must have the same frequency, and also they must have a zero or constant phase difference between them. So there must be a zero or a constant. If there is at all, then it must be constant phase difference. Now, why is it necessary that we are studying this case of coherent sources? We'll be knowing that gradually. But as of now, what are the methods that in which we can obtain these coherent sources is what we are going to discuss. Now, the coherent sources, as you can see, the frequency needs to be the same. And in a given medium, if the frequency is same, then the wavelength must be same as well, because we are dealing with no difference in medium as the light propagates through it. So, as of now, we are concerned about the case of same frequency, which means same wavelength. And because we wish to obtain the same wavelength, it is better to obtain the coherent, or better to obtain the coherent sources from a single source. That's the ideal way of getting it. Now, how do we do that? Now, coherent sources therefore are produced from a single source, and the single source can be obtained by the following methods, one of which we are going to study in detail. But first off, we have, let's say, we consider a source of light over here, and we place a plane mirror just below it or besides it. And what happens is that we get the wave fronts, the ray moves along that direction. There will be multiple rays emanated from that source. We are concerned about just one of those rays, and there will be another ray also going along this direction towards the mirror out of the multiple rays again. And obeying the laws of reflection, the reflected ray moves along that direction. And what happens is that if we produce this backward, we can consider the source, a virtual source, to be over there, just behind the mirror at an equal distance uh, as the original source is from it. And this gives the impression of two sources from a single source. Obviously, there will be a path difference because of the difference in the paths taken up by the rays. But however, the wave fronts that we are going to observe from each of those sources, they are going to interfere with one another, and we are going to end up with an interference pattern. And that is what is important in these cases, that we obtain a proper interference pattern, and that is what coherent sources will help us achieve. And studying those interference, why do we need to study those interference patterns in the first place, that is going to be discussed again uh, as we proceed into the video. Now, this is one way of getting it, and the popular mirror that can be considered the popular method of getting this, or the name that has been given to it, is the Lloyd's single mirror. There's another method of achieving two sources out of one. Uh, it is obviously very effective that we choose the same source. We obtain two sources from one because we have the condition of same frequency or same wavelength. So the second case being that of a source being placed in front of what we call is a biprism. Now, the biprism is a type of prism which has the angle to be very, very big value, that is almost 178 or 179 degrees, which allows the other two angles to be just 1 degree or half a degree. And as a result of that, what happens is that the light emitted from the source, both of them, after getting refracted through it, they tend to move in this manner, and their wave fronts, they tend to interfere with one another, giving us an interference pattern. If we place a screen in front of it, we are always going to end up with an interference pattern on the screens that are placed in front of those interfering waves, and those patterns help us determine various things associated with the wave. Especially that I'm going to discuss is the wavelength is what we actually determine. It's easier in this way. Now, this is the Fresnel's biprism, which is employed to obtain such an interference pattern, such a condition of interference of coherent sources, which are obviously virtual sources. Now you can extend this backward and you end up with two sources which are actually virtual sources, which act as virtual sources. The thing that we have to study in detail is that of a double slit, where we have a point source or a single source, and in front of it we provide a barrier which has two slits. Of course, I have provided you with a magnified view of it. We can take the source a little backward over here so that it's not that close. So this is more or less the source from which the wave fronts, following Huygens principle, of course, the wave fronts which will be considered at those two slits, S1 and S2, you can say, they will be new sources following Huygens wave theory or principles, where the wave fronts will interfere because each point or each slit acts as a new source, and from those sources again those wave fronts are emanated in the forward direction, where they propagate and interfere with one another, as we can see over there. Now, how does this interference pattern evolve is what we are going to discuss, and for that I'll have to consider a proper diagram that I'm going to draw in the next page. So this is the one that I was wanting to show you, related to interference. Now, let's not be too much carried away with uh, the image that we are considering over here, uh, or rather shocked with the image. Uh, Now, here, this one is the source, that is S. And what you see over there are the wave fronts. Now, the wave fronts that I have considered over here, they are the wave fronts due to the, if you consider the first wave video on wave theory that I had drawn, the related to the wave fronts, what I had also mentioned is that the wave front connects all the points which are in phase. Now, if there's a source over here and it is emanating some kind of a wave from it, so this is a wave, a single wave. Now, there will be not a single but many such waves which will be emanated from it, of the same wavelength, of course, from a single source, and that is why we are considering the case of coherency over here. Now, each of those crests, they will be in phase with one another, which is what I have drawn in the case of those blue arcs that you see over there. So those blue arcs, they represent the wavefront that is present on these crests, and the red ones, the dashed lines in the form of the red arcs that I have drawn, they are going to represent those, due to those points which are in phase, and hence the wave front. So this is the wave front due to the troughs. Now, what happens, as I had also mentioned in my previous video, is that when we have the case of a crest going over a crest, or a trough going over a trough. So the case of crest going over a crest, and they're in phase over here. So that leads to constructive interference. While a case of crest interfering with a trough, right, that results in a destructive interference, or lesser intensity is what we are going to achieve in this case. So a higher intensity, or the maximum intensity in this case, a minimum intensity in this case. So what we wish to obtain, or what we do obtain, it's not that we wish to obtain that, what we do obtain is that when those solid curves, or the solid arcs, those blue arcs, when they cross over another blue arc, or we have a red arc, that is a wavefront due to the trough, over a trough, that also results in a constructive interference as well. So in both those cases, you have the case of constructive interference and the destructive interference in case of a crest over a trough. So these wavefronts, whichever wavefront we are considering, this one is for the crest and this one is for the trough. When the crest wavefront superposes with a crest wavefront, and a trough wavefront superposes over a trough wavefront, that is this one, those are the points where we'll be having or achieving a constructive interference, which was the one I have drawn over here. These two green dots that you see over there, if you mark it now, I'm erasing it for you. If you mark them, they are the points where the blue wavefronts, those due to the crests, they have fallen over the blue wavefronts. That means a crest over a crest. And then the next one is that of a trough over a trough. So that again is also constructive. So all those constructive interferences is what I have represented by those green dots. Now consider the case where a blue line falls over a red line. That means the blue line representing the wavefront due to the crest falls on a red line, or vice versa, red over blue. Red, remember, is due to the wavefront of the troughs. Now crest on trough is going to result in a destructive interference, is what we have discussed, and that is what I have represented by those black dots over there. So those black dots represent the points of destructive interference. Now considering the diagram at the top that I have drawn, now this diagram over here has the single source from which we have obtained two sources for using the double slit condition, that is the case of coherency or coherent sources. And what we do over here is that we do not do that, they occur naturally, that when these wavefronts are considered over here for both those sources, the wavefronts, they tend to move or propagate in the forward direction, considering Huygens principle, with the primary resulting in a secondary, and then the secondary becomes the primary itself, resulting in another secondary. And what I have drawn over there are those green dots that I have considered. These are the green dots. These are the green dots. You will have to enlarge the image to see it, or you can try them yourself, which is much more advisable than just looking at the images that are there in your textbooks or that I have drawn, because optics is a subject which you will be able to uh, evolve in easily in your mind when you draw those diagrams and you check for yourself. Basically, that's the case with physics as well. Now, here, as you see, those green dots, they are somewhat aligned. For this line, of course, I have missed out the green dots, but nevertheless, I have considered drawing those rays, or that particular ray, which will be giving me a bright or constructive interference. Now, constructive interference is giving me a brighter intensity or the brightest intensity or the maximum intensity, which is obtained at these spots on the screen. So as you can see, they are aligned so beautifully one after the other in a straight line that you are obtaining this kind of a bright spot, these kind of bright spots on the screen that is placed right in front of it. There will also be dark spots. Now, my request to you is to try out this kind of a diagram that I have drawn over here and see for yourself whether the dark spots are being achieved right between those bright spots. So these will be the spots of the dark spots which will be completely aligned. Now, even though I haven't used uh, any kind of geometrical instrument, I've drawn this with free hand. I would request you to try this out in by using the compass by using the compass box and draw these arcs beautifully equispaced so that you will be able to achieve the diagram in a much more efficient manner than what I have achieved. So, and that will help you understand how these patterns are beautifully formed on the screen. So we have an interference which is redistributing the light intensities between the dark and the bright regions. So actually, as I had already mentioned, that if there were separate waves falling on the screen, then the intensities would have been, if you remember, I've provided that link in this video, that is 2Ka squared. Now, they would have had 2Ka squared at every bit. 2Ka squared here, 2Ka squared here, 2Ka squared here. So this would have been the case with intensity at every point on the screen. What now we achieve is that this 2Ka squared has gone over here. We have achieved a complete maximum intensity, which is the bright spot, and then this 2Ka square, as it has gone over there, there is nothing left over here, so a zero intensity over here, then followed by a maximum intensity, then a minimum intensity with the redistribution, with the redistribution 4Ka squared, then 0. Likewise, you will be achieving the conditions of maximum and minimum intensities on the screen that is provided in front of those sources. Now, it's very important to tell you also that obviously we are dealing with a single wavelength, so we have a monochromatic, which is a single wavelength, definite wavelength. Usually, the sodium vapor lamp is used. Sodium vapor lamp is used, which provides or produces yellow colored light, which is obtained in the form of bright fringes, and obviously the dark spot remains completely dark, devoid of the any kind of wavelength. So this is what we are going to discuss in detail. This is obviously the physics part of it, and you will be amazed to see the exact mathematical proof of it, which is what we are going to discuss in the next video. And that is why this stuff is really amazing, and we have the exact mathematical expression that we can expect, which uh, which really gives complete proof of the theoretical concept that is associated with Huygens principle and the condition of interference. But that is to be discussed in the next video. Till then, thank you for watching. But do try this out, this diagram, and you will be obtaining those bright and dark places on the screen in front of it.